1, 2, 3, 4, 5, 6.
You got
Where we
6.
missing? 1. So I think you're good to
Halfway.
start.
Okay.
Two.
Okay. I'll start the recorder.
Okay. I'll be around.
Yeah, today's the last day.
Today's our day. Unfortunately, yes. Hopefully, I know. But as we said before, you're more than welcome to stay with the kids. I'll reach out to your parents to figure out when you like you could keep them for the rest of the summer. I don't have any problem. You could play with them. And then one of the things I'm going to ask you at the end of today's class, Dr. Broderick is going to give you a link for a survey similar to what we had. And at the beginning, um, good. I'm glad that you liked it. So one of the things is the idea of the survey is we want to be able to run this program, and of course we need to have funding for it and expand it. And this year was a little bit different since we had to do it virtual. But any suggest so the how do you call it? The survey is going to ask you for suggestions. So please, anything that you could suggest, even to make it better virtual, and hopefully next year when we do it again, we could go back around, or maybe we could do a combination of both of them if you think that's a good idea. So any suggestions that you have that you could give us, and then we could use that for feedback. So hopefully we could get more funding for next year. Okay. So as I said, you're more than welcome to stay with the kids. As I said, I make arrangement with your parents to figure out when to pick them up. But you could use them, have them, especially I know the Snap Kids, you could has like what 65 different things that you could do
Oh,
with.
even more than that. It's crazy.
Yeah, so play with it, just don't break it. Then that's it. Ooh, 188?
Yeah.
Holy cow, you're
Yep.
gonna be busy. I mean, holy
Yep.
moly. Okay.
Yep.
But as I said, enjoy it, use it as much as you can. And then when you are, and as I said, I'll contact your parents to return it whenever it's good for you. If you want to keep it for a little bit longer, just let me know, and I'll be okay with that. Okay. So I'll be around, and then please complete the survey and provide as much suggestions, good, bad, whatever input you think of how, if you like this, how we could improve it, both if we do it on ground or if we do it virtually again. Um, maybe we could figure out a way that maybe if we get enough budget, maybe we could do something for the winter break. So yeah, so we could, things like that. Maybe in your suggestions, you could also talk about different topics that you would like to have. Um, so any suggestions
Yeah.
you could think of? Because for example, for us, it was struggling to do something virtual and at the same time something that we knew about. So any suggestions that you have, we will be more than happy to have them. Okay. And and as I said, the more suggestions that we get, we are able to create this. We're able to request for more budget, and then hopefully we'll get to meet again in another opportunity. Okay. So I'll be around. Enjoy with Dr. Broderick, and please don't forget to fill out your survey. Okay. Talk to you soon. Bye.
Yeah. Whenever I meet all of you, you're gonna have to remind me that this is where I know you from because I don't know what any of you look like. So, by all means, I hope that happens and just say, hey, I was in the online summer thing. I'd love for that to happen. All right, I went Star Trek today. Am I backwards? I'm not backwards. I went Star Trek today. Sorry. I think I'm probably more of a Trekkie at heart, so that was my choice. Let's see here. We left off yesterday. I think we were talking about the voltage dividers. Oh yeah, we definitely are. I'm recording the video. That was just to me. Yep. So I've got the recorder on. We'll post it. It'll look just like my feed. I'm just recording it off of what you see in my camera. So I think the quality will be a lot better than recording the WebEx window, but you don't get the text feed and things like that, unfortunately. Let's see what we're doing today. Let me slide you all up here. Make some room. So we left off yesterday talking. Oh, I don't think that was. I think Chase is still not muted. My audio sounds like a robot. That's no good. What if I sound like a robot? Okay. So I have some people saying I sound like a robot and some people saying I don't. Okay. All I'll suggest is watch the video afterwards. I don't know how to fix that from my end. Since it's you by yourself, I'm sorry. I hope you can get it sorted out. It might be bandwidth on your end, my best guess. And it'd be cool if I could get closed captions, but I don't think I know how to do that. Okay, so we left off talking about the voltage divider yesterday, and we built a couple simple voltage dividers and did the calculation and validated that with the snap circuits. I want to talk about one more type of component today because we're going to use it in a few of the circuits. Actually, we're going to talk about two more types. We're going to start by talking about capacitors. Then we'll move on to transistors and we'll build some amplifier circuits. I'd love to hear what I sound like a robot. I don't know that we'll get time to build any of the IC circuits, but I can talk to you a little bit about them at the tail end, and we'll definitely not have enough time to get to digital circuits, which I think would be really cool. I'd love to do that with you, but perhaps another time. Come take a class from me. I would love that. Okay, so let's get going with capacitors. Okay. All right, so we've mainly been talking about resistors as our passive components. Capacitors are also passive components in that they can't add energy to the circuit, but just because they can't add energy doesn't mean they don't have anything to do with energy. We can use capacitors to store energy. Okay, so if we can put energy into the circuit at a time that's convenient, and then draw it back out of the circuit when we need that extra energy, we can do that with a capacitor. It's really useful. So it's a passive element, but it's also one of the two storage elements. The first one being the capacitor, okay, which sometimes we just call a cap, and the other one is an inductor. Okay, also useful. We won't get to it today, but it's the other passive element, and it's also a storage element like a capacitor. Okay, so the capacitor stores that energy in an electric field. So we build it by taking two plates and putting them in parallel to each other, just like I have drawn there. So they should be conductive plates. You can build them out of aluminum foil. I think that would be kind of a neat project to do some arts and crafts and build a capacitor. So you build two plates and you separate them by something that's an insulator. So it's not going to allow charge to pass through. And in this instance, we call that insulator the dielectric. Yeah, you can use paper. Yeah, the dielectric can be all sorts of materials. It can be air, for that matter, as long as it's separated. So you can use paper. You can use Teflon is a really good dielectric. Polypropylene is another really good one. So all sorts of materials. Polypropylene is like a styrofoam material. But it's kind of like when you were playing with magnets, where the positive charge attracts the negative charge, and that's what's going to happen. So if I put a voltage across the two plates of the capacitor, we're going to use the snap circuits today, almost exclusively. So if I put a voltage across the two plates of the capacitor, there becomes this charge differential. So all the positive charge collects up here on what I have drawn as the top plate, and all the negative charge down here, all these electrons, collect down here, and they're attracted to each other. And they're attracted to each other more strongly if the plates are really close together. So the game is getting the dielectric thin enough so that the plates are really, really close together, but not so thin that the charge is going to shoot through the dielectric. Okay, so there's this balancing act of how do I get a really big capacitance by putting the plates close together, and and still having a really good insulator in between so that they can't conduct directly to each other. The other thing we can do to make the capacitor bigger is just have more surface area. So let me grab a prop. If I can find it. Here we go. So let me get big. So you have this. Oh, and of course it's green for my green screen. Okay. Well, you have this capacitor. Okay, and it's round. So the reason it's round is the two plates are rolled up. So inside that capacitor, to get more surface area so that we can cram more charge onto those two plates, it's rolled up inside. So you might have a roll like that, and then on either side, let's see how fine my pen control is. Should probably draw this. On one side of that dielectric, you have one plate, and then on the other side of the dielectric, you have another plate. Okay, and there might be an additional insulator in there. I think there has to be, to prevent the red from touching the blue. Okay, so you take the two plates and then you just start at one end, you know, kind of like you're rolling up a sleeping bag. You can only see me. Oh, of course, yeah. Still getting used to this game. Thank you. Sorry about that. Okay, so it's a roll like that. Okay, so take the two plates and just roll it up from the end. And that's how you get more surface area to make more capacitance. Okay, let me see, grab my notes here. Okay, so it's kind of like playing with your magnets growing up. The north would attract the south, right? The positive attracts the negative, but it's sort of an electric field, not a magnetic field. So similar concept, a little bit different underlying physics. But we can store energy that way. If I remove this battery, in a perfect world, the positive charge is going to stay there and the negative charge is going to stay there because they're going to attract each other. They're only going to recombine when I give it another circuit that can cause them to meet in the middle and recombine. That's in a perfect world. There's a little bit of resistance. Actually, there's a lot of resistance within the dielectric. So there is a path for them to recombine, and they usually do it slowly, and we call that leakage current. So it will draw itself down over a period of time. If you want to look at the quantity of charge, denoted as Q here, so we use Q as a variable for charge. You can say the charge on each of the plates is the voltage times the capacitance. So the bigger the capacitor, the more charge I can fit, and the higher the voltage, the harder I'm pushing, since it's the force in electric circuits. And if I'm pushing harder, I can cram more charge onto each of the plates. Okay, so Q equals VC if you want to figure that out. I call that the home shopping network equation, and that's just how I've remembered it since I learned it a long time ago. Okay, so let's build a little circuit so that we can start to play with charge. So this is going to be in the snap circuits. I have pictures for you. And it's going to be a fairly simple one. We're going to use the diode again. And that way we can see how bright it is and what's going on there. Okay, so battery, the 100 ohm resistor. So there's two resistors. Just make sure you grab the 100 ohm. And then I added this component in here, and it's going to allow us to switch the circuit on and off, and the LED on and off, not quickly but easily, so that you don't have to connect and disconnect things. This schematic symbol, it's a pretty simple schematic symbol. It just has this angle up here, and it shows it's broken, and we call it a single pole, single throw switch. Okay, so there's single pole means that it can switch one signal, and single throw means there's one position where it's connected to the circuit, to the other path. Okay, so this is just really inside all it is a wire touching another wire. Okay, but it's a switch, not a button, so you can leave it in that position. And that one, I have it already built into another circuit. There we go. So that one looks like that. Oh, again, the green screen killing me. Okay, so it's a switch, so it stays in whatever position you put it in. Okay, and it's got the little schematic symbol behind it as well, which is kind of cool about the snap circuits. Put it back where I found it. So I've added that so we can turn it on and off. The solar kit, I'm not saying you have to go pull this out, but I thought it was a good example, and you have it physically in your hands, which is great. Has a dual pole, dual throw switch, just as an example of the terminology. So we call that DP-DT. And if you go buy them, go check it out on DigiKey. If you want to buy a switch, it'll say single pole, dual throw. You can have single pole, dual throw. This one's a dual pole, dual pole, dual throw. So you can see it's got 6 connections down here instead of just 2. And if you connect a signal here, you can slide the switch to connect either up here or down there. And then you can do the same with the row that's down here as well. So I can connect a signal going in here, and then switch decides whether it connects to the right or it connects to the left. So that's a dual pole, dual throw. It can switch 2 signals, and it has 2 places it can switch it to. So we're going to do a switch for the first time. So here's the little circuit I want you to build. So starting with the batteries, through the resistor, there's the switch. And then I use these little, they're the little blocks that say 3 on them. Is that an R1 or 2 next to switch 1? Oh, I don't know. It's the 100 ohm. I can tell you that. It's not 3. R1. Okay, let me note that. All right, so that's R1. Okay, fair enough. So I use these little 3 blocks. We're going to add the capacitor in there very, very quickly thereafter. So I left a place for the capacitor, and then I got lazy and I put the black wire in there because I didn't want to like do snap circuit origami to get it all the way down to the negative side of the terminal. Okay. Okay, so once you have that wired up, open and close the switch. Okay, and just see what happens to the LED. Mostly we're looking at how quickly the LED turns on and off. And make those separate observations. How quickly does it turn on, and how quickly does it turn off? So do it a few times. Hey! Your battery died. Oh, you left it plugged in? Do you have other batteries? You can try to pull out the batteries from the solar kit. They're a little bit lower voltage, but we are going to need all 4. Okay, seems like immediate when turning off and a small delay when turning it back on. Okay. So that's a worthwhile observation. I'm a little surprised by the small delay turning on, but that's okay. That's what you observed. Immediate when turning off is what I'd expect. Best place to find double A's in a house is go steal a remote control from the TV. Don't tell your parents. My kids do it to me all the time. Yep. Just as I get comfortable and I sit down to watch TV, doesn't work. Okay, Sham's got it to turn on. We've got, so hopefully a handful of you have seen what happens when you turn it on and off. Okay. So we can go with Josiah's observation. Okay. Because the component... Did we do this? We did it without the switch. But today I'm adding the switch so that we can play with the capacitor a little bit. Okay, so I want you to observe what happens without the capacitor and what happens with the capacitor, just to show you that it's in fact storing energy, which is its whole purpose in life is to store energy. I wish my purpose was that clear. Okay, so let's see. So let's scroll down here. Okay, so if you got that working and you see that you turn it on, you turn it off, it should be pretty quick to do both. It sounds like there was a little bit of delay for Josiah. I want you to add a capacitor, and I want you to add the 470 microfarad capacitor. And I know what you're going to ask. You're going to say, is it C1? Oh, it looks like it's C5. I can see it in the picture behind my head. There we go. That glare is off the snap kit, not off my head. So the 470 microfarad, I chose that one because it was the biggest that we had. Okay, so it kind of makes the effect as prominent as possible, and that's why I left those two parts. So on the schematic, I would draw it this way, and I'd be putting it in parallel with the diode. On the snap circuit kit, I would snap it into those two extra places, and it's also in parallel, right? It shares the same two nodes. So over here we can see it shares this node, and it shares the node on the bottom, and then over here we can see that they're both snapped into those three rails, so they're in parallel. Okay, so if we do that, okay, give that a try, and then make the same observations. Turn the switch off, turn it on, turn it off, turn it on, and see what happens. And then let me know. Turns off instantly, slowly fades away when off. Starts to fade when you turn the switch off rather than shutting it off. Yeah, okay. And that's exactly what I was hoping you would see. And that's because when the switch is connected, the capacitor charges to whatever voltage is across it. Okay, so this 3 volts is going to send current through the diode. I think we measured that diode to be around 2 volts yesterday. That was like a whole 24 hours ago. So hopefully I remember that number correctly. So when the switch is closed, you're going to see about 2 volts across here. And that's in parallel with the capacitor. When you open the switch, this 3 volts is gone, and the diode is going to start to pull some of the charge off. So that positive charge on the top plate is going to start to recombine with the negative charge on the bottom plate. And as it does that, as the charge starts to recombine, Q gets smaller, and as Q gets smaller, the voltage across it gets smaller. And ultimately, it drops below the voltage needed to turn on that diode. Okay, so but it takes a little bit of time, and that's what the capacitor can do. It can buy us a little bit of time if we have a loss of power. Okay, all my computers are running off of a UPS, uninterruptible power supply. That's using a battery, but I promise you there's some capacitors in there to pick up the short-term change in energy delivered to the power supply. Okay, in that way, the capacitor acts as a filter, and in this position, it's really filtering high-speed changes. So without it, you cut off the switch and you see it in the LED immediately. With this, you cut off the switch and the capacitor starts to decay in voltage, but slowly. Okay, so the high frequency change in the switch looks like a lower frequency signal for the voltage across the diode. Okay, and it's doing that by storing energy. All right. So, I guess we should do this, right? Feeling okay about capacitors? As far as storage elements, we didn't really do. I like 4, 3-ish. 3-ish is cool. There's a lot more to them. Like if you want to filter AC signals, they're also really useful. If you want to filter my voice, you could figure out what frequency is going to pass through a particular capacitor, and you can build filters out of it, which is great. So 3 and 4-ish, I'll take it. Okay. So super important. We're gonna use them in a couple other circuits today. So that's why I wanted to start the day talking about them. All right. Let's see. Where do we go from here? Let's leave that one up. Let's come back over here. And that's capacitors. All right. Save it. Sure. I probably wrote something on it. Oh, come on now. Where's Friday? Here's Friday. Okay. So the other component that I want to talk about, tres. I'll take tres. The other component that I want to talk about is it kind of revolutionized the world. I get a little poetic about this one. It makes the world go round. We've reorganized society based off of this component, which is, I don't know if I want to have that big an impact on the world, but you got to say, like, it's a pretty neat thing to have done. So there were 3 guys that ended up coming up with the transistor. The most notable is Shockley. I can't remember the other 2 guys. Shockley was the guy that came up with the idea, and then the other 2 guys actually made it work. Shockley couldn't make it work at first. So I like to give them a shout out because they get forgotten to history a lot. And of course I can't remember their names. So But this was 30s, 40s, back in the 1900s. And ever since then, we've just been making it smaller and using it in just about everything we do. Your computer is built out of them for the most part. And if your computer is, so's your phone nowadays. Okay, gone are the days where you have an old analog phone. My microwave has transistors in it. Even my toaster does, which just frustrates me. I kind of miss when it was a dial and you hit the button and it was a little mechanical timer. Now it has a separate clock that I have to set, and if it has that digital clock, it's got transistors in it. Okay, the list goes on and on and on and on. So everything we do nowadays involves transistors. They're all around us. They're allowing us to meet virtually right now. So I think that's a pretty cool thing. I think when we teach transistors, for the most part, we launch into, well, it's a semiconductor. It's made out of silicon. It can be made out of other stuff, and it's got little bits of phosphorus and it's got little bits of boron, and we start talking about how the charge moves and things like that. And I think we miss the big picture of transistors. And the big picture of transistors is that it's a switch. It turns on, it turns off, and what makes it useful for some other applications is that it can be somewhere in the middle. So unlike the slide switch, okay, unlike the single pole, single throw switch that we had in that diode circuit, the transistor can be somewhere in the middle. Okay, when this one's off, I would call it an open circuit, so no current can flow through. It has close to infinite resistance, so we say it's infinite ohms, okay, as I have written here. And if I slide it over, we would call it a short circuit, which is a bit of a misnomer, but it just means that it's connected, and it would have 0 ohms and no resistance. For the transistor, we call those two situations, when it's saturated, it's 0 ohms. We call that saturation. Okay, and there's a really physicsy reason for that. We're saturating the depletion region with charge carriers. Like I said, I don't like to talk about that early on. We can talk about that later if you want, or you can go take the class. I don't teach that one, but I would love to. But we saturate it, and that means that the switch is closed so that current can flow. When it's open, we call it cutoff. Okay, we're cutting off the flow of current. I think that one's a little more intuitive. Is that what logic gates are made of? Yeah, some logic gates are. Do I have that book? I have a wonderful. Oh, Casper, I think you would get a kick out of this book. It's on the other side of the room, but it's a book about building processors from discrete components, and some transistors are better than others for building logic gates. So when logic gates were first introduced, we built them out of what's called a BJT transistor, and that's what we're going to play with today. That's what you have in the Snap Circuit kit, so that's what we can play with. And you can build a simple NOT gate out of that transistor, which might be kind of fun to try to do out of the components you have there. But if you want to build a better one, you need a few more transistors. The problem comes from power consumption. So with BJT transistors, like we're going to play with today, it's just going to suck your battery dry. Yep. Was it the Minecraft update? What is it called? Redstone? Something like that? No. Okay. I've seen people build computers in there and stuff like that. I think that's awesome. Then I'm gonna. Okay, then I have a suggestion for you. This one, MHRD. If you're into that and you spent 3 weeks doing it, it sounds like you have too much time on your hands, first off, and I'm totally jealous that you have that time. But the game that I like, that's just is MHRD. Let me send that to everybody. It's actually a pretty neat little simulator to build logic gates and design your own processor, but it's gamified so that you get specifications and you have to complete the circuit for that specification. I've been having fun playing with that one when I should be doing other things, but I think it's also a useful teaching tool. So if you're into logic gates, search that game. It's on Steam, and I think you can also get it directly from the publisher or the game developer, which is pretty cool. It's not that expensive. Anyhow, so yeah, we absolutely build logic gates out of that, and because we build logic gates out of it, we build processors, and we can build memory and all of the components that are necessary for designing your computer. Okay, so saturation and cutoff, that's what we're going to use when we use digital circuits. There's another type of transistor called a complementary metal oxide semiconductor, CMOS, and that one doesn't use as much power. So nowadays, what's probably in your phone and in your computer, they're all going to be CMOS transistors. The kit didn't come with those. We're not going to play with them, but it all comes down to power consumption. So both of them work for logic gates because they're both switches. We turn on and off the output using a lower powered signal on the input. Okay, the BJTs are still pretty useful for building what I would call an analog circuit. So it's not switching between two discrete states. It can take on some value in the middle, and we can use those to build amplifiers. Okay, so when I say it can be on, it can be off, and it can be somewhere in the middle. Well, when it's somewhere in the middle, really what we're doing is creating a voltage divider somewhere in the circuit. That's why I wanted to talk about voltage dividers yesterday. We're creating a voltage divider somewhere in the circuit, and we're using a really low-powered signal, maybe from a microphone, or today we're going to use, you can, if you have it, I hope you have like an MP3 player or a cell phone, something that you can play audio out of. You're all on PCs that probably have audio cards, worst case. But we can build a little amplifier out of that transistor. So if it's not a short circuit and it's not an open circuit, it's somewhere in the middle, and we call that the active region. Okay. So that's my, like, I usually say 30-second spiel, but that was way longer than 30 seconds. That's my short introduction to transistors. It can be on, it can be off, it can be somewhere in the middle. It's really just a resistance that's varying from 0 ohms to infinite ohms, and it's all based off of something else happening in the circuit. For a BJT, bipolar junction transistor, it's based off of a current, and for a FET or a CMOS set of transistors, it's based off of a voltage. So, but they're all transistors, and they all switch on and off. So this one's a BJT, bipolar junction transistor. So maybe I should write that. This one over here. So this is a we'll go with red, sure. Bipolar junction transistor. Okay, BJT. So I'll say BJT without thinking about it. It's just in my jargon and vocabulary. So this is the schematic symbol for a BJT transistor. And then I went and I grabbed some different pictures of BJT transistors in different packaging. This might not actually be a transistor, but it has the same package. I just looked at the part number, and I think that's actually an op amp. Anyhow, so there's 3 terminals, which is something new, that we have components with 3 terminals, and they come in different sizes. We'd like to make it as small as possible, so the TO92 is probably the smallest of the 3 that I have pictured here, but there's no place for heat to conduct off of it. And if we're dissipating power, and I said the BJTs are bad because in the sense that they dissipate more power, there's no place for that heat to go, or there's no good path for the heat to be conducted off of the component. The TO220 is a little bigger, and this white part in the back here is usually metal, and that metal part can be screwed onto a heat sink, some big chunk of metal with fins on it that allows good airflow, and so we can get some heat away from it that way. So we can usually drive a bigger speaker if you're building an amplifier with something like that, because we can push more current through it, dissipate more power, and not have it overheat and go pop. So a lot of stereos, I spent part of my undergraduate career repairing stereos to try to pay for college, and a lot of the stereos I repaired had these on the outputs, that type of transistor, and I replaced a lot of them. So it's a pretty common package. Transistors aren't the only things that come in these packages, but these are common packages that you will find transistors in. You'll find voltage regulators in a TO220 very frequently. The TO3 is a bit of an older package, but it has even better thermal characteristics, just because it's bigger for one, and it has much more surface area, and the casing's all metal, so you can really get a heat sink pressed up against it to draw the heat away from it. So you may see all three types of those. In a schematic, it's going to look like that, and I'm not going to pull up the snap kit one because it's buried in a circuit that I built for later. But it has this symbol, and it's kind of one of those triangular pieces. It's a red triangular piece. And we usually use, does it say Q on it? Yeah, it says Q on it. So we usually use Q to indicate that the component is a transistor. The whole point of this transistor is to switch on and off, and with a BJT, we switch it on and off by controlling this current. Okay, so from the base to the collector. Oh my gosh, I have those backwards. Hold on. Ready? Editing on the fly. This is the collector. And this is the emitter. Can we pretend that didn't happen? My bad. Okay, so collector, base, emitter. So from the base to the emitter, that current is usually really small. So that's going to be what's coming out of a microphone or a sensor, and it's going to be really tiny. It might be microamps. Okay, so millions of amps. And it's going to switch this current going from the collector to the emitter, and that one's usually going to be bigger. If it's a TO92, it might only be in the milliamps, but I'm using a microamp signal to switch a milliamp signal, so I'm amplifying it. So I have this small current controlling this large current. Okay. So we're going to build a circuit, and I went a little crazy here, so there's a lot to unpack, but this is the circuit you're going to build, and we're going to start off by having it switch the diode on and off, but we're going to use a low current signal to switch the high current diode. Okay, so when you build the circuit, it's the same circuit. The only difference between the left and the right is whether or not the button is pressed. Let's see if I can find that button. There it is. So this one is switch 2. It looks something like that. Okay. And this one is a normally open button. So we would label it NO for normally open. You can buy them as NC, normally closed. Okay, and all that refers to is what's the state of the button when I'm not pressing it. So this button is open when I'm not pressing it. And that means no current can flow through it. Okay, so because no current can flow through it there's no current entering the base, and then this transistor is going to be in cutoff. Okay, so it can be open, it can be closed, it can be somewhere in the middle, right? So if it's in cutoff, there's going to be no current flowing from the collector to the emitter. Okay, if there's no current flowing through there, then the diode's not going to turn on. Fair enough. Okay, now the magic happens when you press the button. You press the button, and now it's closed. It's not normally closed, it's just closed. So I drew it this way, which is a bit of a kludge. This is the schematic symbol for a normally open button. I just wanted you to, in your heads, think, okay, now I press it down, it makes the connection, and current can flow. So we can use a little bit of Kirchhoff's voltage law. Let me get this out from behind my head as much as I can. I might disappear for a few seconds if I have to. Where yesterday we knew that we measured that the voltage across the diode when it was forward biased was around 2 volts. Okay, the base emitter junction of the BJT transistor makes another diode. It's internally, it's another diode. There's something else going on, but we can think of that connection as a diode, and it's got the little arrow. So it also has a forward bias voltage, and it's usually around 0.7. We usually assume it to be 0.7. So I have plus and minus 0.7 volts up here. I have plus and minus 2 volts here. And then on this side, I have the 3 volt, right? So the path that I took, as I wrote in my head, I wrote my equation for the KVL. I wanted to figure out this voltage. Okay, so if I know what this is going to be, roughly, and I want to find that resistor voltage, I can take the path around the circuit here and write the KVL. So I went up 2 volts, I went up 7 volts, I went up, at the time it was an unknown voltage, but I go up 0.3 volts, and then as I come over here, long bar is positive, short bar is negative, I drop 3, and I'm back to where I started, so it's 0. Okay, so KVL is still going to hold in these circuits. We don't get away from that. It's a law. Okay, thanks to our crazy old dead Prussian guy. So that's how I figured out that voltage there. This is the forward bias voltage of the LED. This is a typical value for a forward bias voltage of a silicon BJT. And then whatever's left over is going to be over here. Okay, so when the button's pressed, I'm going to make myself disappear just so you can see what's behind me. When the button's pressed, I've got 0.3 volts across the 5.1K. Okay, and that 5.1K gets divided into the 0.3 volts. This is all just Ohm's law. And we've got 58.8 microamps flowing here. Okay. When we do the same thing over here, we're going to assume it's in saturation. That's enough current that I think this one's in saturation, and the way it's behaving kind of tells me it is. I get the 2 volts here. That leaves me with 1 volt if I'm following the path around this way. Okay, so I go up 2. This one's actually 0 volts because it's saturated. Okay, there's no resistance, there can't be any voltage across it. I go up the last volt, I come back down with 3. So there's 1 volt across that 100 ohm. So I take the 1 volt and the 100 ohm and divide them, and I end up with 10 milliamps. Okay, so the small current over here is controlling the large current over here. So this is a circuit. I might not use this exact circuit. I might use a FET instead of a BJT, which is the other type of transistor. But this is a circuit that I use, this type of circuit. I use it when I'm working with microcontrollers and I need to switch a big load. So if I have the small signal coming out of a microcontroller and I need to switch a motor, or I need to switch an LED, even might be too much for the microcontroller. I take the signal from the microcontroller and I I would put it on the base, and then I would use the transistor to switch on and off the current path for the larger load thing. So, so it's a pretty common thing. Okay, so let's build it. If you haven't started already, take a few moments. It's not going to be too exciting, honestly, because it just looks like an LED turning on and off with a button. But as you're doing it, think about the small current flowing through here, and that's controlling the big current flowing down here. And the big current's the one that's actually going to turn it on. So go ahead and give that a try. Oh, I don't know that emoji. Sorry, Juliana. It turns out I'm old and not hip anymore. Okay, Casper was done before I even started, so let me know when you get it working. Button go brr, yep. Kind of drives me crazy that the battery's on the right. We usually try to have power on the left, but it worked out. Does it turn on, Shams? Rotate the image. Is it backwards? Is the image backwards? Oh, to get the... Yeah. Gotcha. Yep, perfect. Perfect. Okay, so that's your first transistor circuit, so which is good. We usually don't get to that until like junior year. We do a lot more detail in between now and then, but that's pretty good. I like it. Okay, Shams is good. Got a smaller group today. And some of you are the quiet ones, which is fine. Juan got it. Cool. Josiah got it. Cool. Awesome. Okay. So, so it's a switch, okay, and it's turning the signal on and off. It's really useful for interfacing low power circuits to high power circuits. If you go buy a motor controller, there's a good chance that it's going to have at least 4 transistors in it. And I think it's kind of a cool circuit, so I kind of want to briefly talk about another way to use these transistors now that you have some feeling for what the transistor is doing. Okay, so let's grab a fresh sheet. Okay, so just like with the circuit you just built, we can take the other type of transistor called a FET, and I'm just going to draw this with a FET because that's usually the transistor that's used for this. You can take 4 FETs, okay, but the concept is the same. I'm controlling whether this is on or off, just like it's a switch. You can take 4 FETs. I'm trying to draw this nice because I'm going to copy it and then mark it up different ways. and connect it this way. A lot of the circuits I build when I'm working on robotics and I'm working on any kind of automation project. And that's what I do when I'm consulting nowadays. Probably doesn't have a positive and negative supply. So it might not have plus 15 volts and minus 15 volts. It probably has a single DC supply that we can use to rotate the motor. Okay, so we would connect it like this. Okay, so these are all FETs, and we can control whether they turn on and off, and we control whether they turn on or off by putting them in saturation or putting them in cutoff. Okay, with a FET you do it with a voltage, with the BJT you do it with a current. That's kind of the big difference between the two. There's a lot of other little differences, but that's the big difference. So we're controlling whether these are on and off, and we create these two paths, and then in between we put the motor. Okay, so we stick the motor in here. Like that. Okay, and we'll put the M there for motor, and then this is some DC voltage that we're controlling. Okay, so let me take a quick copy of this. With only one voltage, we can only spin the motor one way, just like we did with the fan, right? To switch the direction of the fan, we had to switch the direction of the current flowing through it, and we did that by taking the two wires and swapping them. So that's okay if you only needed to change once in a while, and you can intervene and just take the plug and flip it around. That would be fine. That would work out great. But if you're trying to control anything that's robotic, you know, and you spin a motor and you want an arm to go one direction, and then you know that you have to bring that arm back the other direction without having to intervene and rewire the circuit, you're probably doing that with this circuit, and it's called an H-bridge circuit. And it's rather clever, and it's a great use of transistors to interface low power signals from a microcontroller that would be injected here at these 4 points, and we can control the high power signal going through the motor, and that's what's going to do the work. Okay, so if I want it to rotate one way, we turn this one on. Okay, so let's turn this one on. So we put it in saturation. Okay. And then we turn these off. Okay, and this would be cut off. Okay, and in doing that, the way the current flows through this circuit is out of the battery or whatever is supplying the power down here through this transistor, because it's the one that's on, through the motor, and we're going left to right. Okay, going left to right. Down through this one, because again that's the one that's on, and then back to the battery, so we complete the circuit that way. Okay, so this one's going left to right, and that's going to make the motor spin one way. Okay, I think you see where I'm going. I'm guessing you see where I'm going with this. If not, let's just go do it. Okay, so if I want the motor to spin the other way, we just flip-flop here. Okay, so this one's now going to be on, and this one's on, and this one's off, and this one's off. I should have used green and red like a stoplight, but hindsight. Okay, so now the current's going to go over here, and since this transistor's on, It's going to flow through here, through the motor, down through this transistor that's on in saturation, and then back up. Okay. And as it goes through the motor, now it's going right to left. So it's going to spin the motor the other way. Right to left. Okay. And I can control all those signals with a microcontroller. Okay, and I can use the really tiny digital signal out to switch all of these on and off, and I can use it to control the motor, control the direction. There's a really clever way to not just have it be on and off. You can turn it on and off really quickly, something called pulse width modulation, and then you can control the speed of the motor as well, which is also very, very useful. So this is just a nice application that you may run into if you're doing anything robotic. You're going to deal with H-bridges. You can buy them on Amazon nowadays, which was just unheard of when I started playing with robotics. That you could just like go buy an H-bridge, but it's a really neat circuit. There's some other details to it. How do you drive these into saturation and cutoff that get a little more complicated, but we can dig into those another day when you take my class. Okay. Let's see. How are we? Let me see here. How are we feeling about transistors in regards to them shutting on and off? Saturation and cutoff and what they're used for. 2/5. She's just playing with my... Oh, 2 out of 5. 2 out of 5. Okay. Sorry, Juliana. 4... 3, okay. I got a range. I can do better. That 2 hurts, but that's on me. That's not on you. Okay. 2 out of 8. Uh-oh. Now he's really messing with me. Okay. Or he could have meant 5. All right. Well, let's play with our next circuit and see where that gets us. But I think it's the more complicated of the circuits. Okay, so I was not planning on this, but I thought it was a nice thing to talk about. So let's do this. Save that for distribution later. And let's go find Friday. We're not on my last one already, are we? Ooh, we are. Uh-oh. Uh-oh. Okay. Well, this is probably our most complicated circuit. Yep. So this is probably the most complicated circuit we'll build as a group. And that's okay. It gets pretty messy. But I want to talk about the third state that we get into with transistors. So we can turn it off, we can turn it on, or it can be somewhere in the middle. Okay, so we're going to build an audio amplifier. And I built this, and I stole my daughter's MP3 player, and I played some of her music through it. So that's that big circuit that I have. Behind me, I have pictures of it. I have a schematic of it. But this one's actually a Snap Kit. This one's actually a Snap Kit schematic that I took from them. But what I did was I drew it as a schematic because I think it takes some practice to say this is the physical realization of something and this is the schematic representation of it. So here's the schematic representation of what I'm going to have you build in a moment. So we need both sets of batteries just to get the voltage up to where we want. We have our single pole, single throw switch. That way Juliana's batteries don't wear out overnight if you remember to turn it off. So this one again is single pole, single throw. And that's really just an on-off. I take issue with one of the things the SnapKit manual says. I don't think they're giving you the complete picture, so I'll try to rectify that. But the heart of this amplifier is this simple transistor right here. Okay, same transistor you used to just turn on and off the LED. But now we're going to use this transistor to be somewhere in the middle. It's not going to be a short. It's not going to be an open. It's going to be somewhere in the middle. And we're actually going to take the multimeter from the Solar Labs kit, and we're going to make sure it's somewhere in the middle. And I'll explain why we want to do that in a moment. So when this transistor is on, current is flowing through the speaker. When this transistor is off, there's no current flowing through the speaker. Okay, so that's how we're going to take the speaker and get it to push in and out. And if we do that with an audio signal, we'll be able to hear it. Okay, so that's your schematic symbol for a speaker. Here's the BJT. And we have a potentiometer over here. It's wired in a way that drives me a little crazy, but it's functional. And remember, that was a resistor that we can change the value by moving the slider up and down. And we're going to use that to turn the transistor on to the right amount. Okay, we don't want it off all the way. We don't want it on all the way. We got to make sure it's just turned on in the right amount so that we can get a clean audio signal out of it. The other thing we're going to use is this capacitor, and we're going to use that to block any DC voltage. So we'll get into that as well. So this is the schematic representation. The heart of it is the transistor, and we're using that transistor to form a voltage divider. So this section here, we have 6 volts across it, right? And really what we want to know is what's the voltage across the speaker, because the voltage across the speaker is going to be the signal that we hear as music. Okay, so I took that and I thought of it as our voltage divider. Okay, so I drew it with this 6 volt thing here, which I don't think I've drawn for you, but it's another way to indicate a voltage, and it's that 6 volts is always in reference to ground. You might be more comfortable, since I've been drawing them this week, this way. Okay. That's what's going on, and that kind of looks like our voltage divider. I'm hoping that that's coming back to you from yesterday or the day before. I think it was yesterday. All right. The current is what's driving the speaker, but I think of the speaker just as a resistance. There's some inductance to it as well. But whatever that current is fixed. So go pick up a speaker. Maybe you can even, we can see it on this one too. So here's the SnapKit speaker that we're going to use. And if you flip it over on the back, it says 32 ohms. So there's actually a resistance on that one. That one's 32 ohms. That's pretty cool. I hadn't realized that it was labeled, but most speakers are. So I should have looked, and the casing is clear so you can actually see it. So there's some resistance to this, and it's fixed. It's so fixed that they stamped it right on the back. Uh-oh. I broke my circuit. I'll fix that later. How did I do that? Oh, I stole the switch too. The switch is missing. The transistor is going to form a variable resistance. Okay, that resistance is going to change. So we put the slanted line through it, and that indicates that it's going to change. As that changes, the voltage divider is going to change. If this became 0 ohms, it would be connected to ground. So the speaker would have all 6 volts across it. If this becomes an open, then no current's going to flow. And if no current's flowing, then there's 0 volts across the speaker. So we can vary the voltage across the speaker as much as the supply allows us to, but no further. And that's going to become a problem for us. And that's what the potentiometer is going to help us figure out. So So we have to pick that transistor carefully, and we have to set it up just right so that we can get the audio signal out. Okay, did I write these correctly? Base, emitter, current. Yep. So the transistor resistance, okay, so the resistance between this point up here and this point down here, the collector emitter resistance, is going to be controlled by the current flowing through the base and emitter. Okay? So that's our game. That's how we're building an amplifier. We're using a small signal to control a big signal. The potentiometer we have to set to avoid clipping. So we want all of the signal to pass through. It's going to look like a sine wave. So if you've taken pre-cal, you've probably dealt with some sine waves. And we want to make sure the signal that we put into the circuit comes out of the circuit and without being altered as much as possible. Because if we alter it, we introduce some distortion, and you can actually create some distortion with this circuit. Okay, so we're going to set the potentiometer so that just the right amount of current is flowing through here. Okay, we need this voltage to be high enough that the transistor actually turns on. And ideally, we're going to set the voltage from here to here. Come on. Come on. Give me that color. Okay. Ideally, we're going to set this voltage from here to here to be 3 volts. Okay, because that's half of the total 6. It's dead center. And that way the speaker can push the same amount out as it can be pulled back in when that voltage starts to vary and create the sound wave. Okay, so the way we do that is we adjust this pot. We adjust that resistance until we see what we want for a voltage there. And that's how we're going to set the biasing correctly. In the snap kit circuit, it says it's the volume. I got to tell you, I played with it, and what happened was the volume didn't change that much. But what did change was when I had the biasing wrong, I could hear the clipping in the waveform. So it becomes really distorted. Maybe not robotic like Juliana said I sounded like earlier, but you'll know it when you hear it. It'll sound like garbage. Okay, so that's the role of the pot in the circuit. Okay, the role of the capacitor is to couple the signal, block any DC. Sometimes when we have a capacitor in a particular position in a circuit, we give it a special name. And that's all we're doing here. It's not a capacitor that's you go and buy called a coupling capacitor. It's a capacitor that has a particular role in a circuit. It's connected in a particular way. It's coupling the audio signal that we're going to put in at the audio jack up here to the rest of the circuit. And by coupling, I mean it's removing all of the DC. It's not allowing any DC voltage to pass through here. It's only allowing higher frequency AC signals, like my voice or the music coming out of an MP3 player or something like that. Okay, so that's the role of the capacitor. There's the schematic symbol for a capacitor. I'm not sure if I've written one for you. And then we also have the schematic symbol for the audio jack. Okay, the outside of the audio jack is connected to what I'm thinking of as the ground of the circuit, and then the tip of it, not sure if you can see this, maybe I should have taken a picture. Okay, the tip of it has a separate conductor connected to it. So this one actually has 3. This came out of the snap kit circuit, and you can use it today to hook up your phone through this amplifier. It's got 3, so I would call this one a tip ring sleeve connector. It's got a tip, It's got a ring in the center, and then on the bottom it's got a sleeve. So I can pass 3 signals with this type of connector. And we want to do 3 for audio because we need a ground so that we have a reference point, and then we have a left channel and a right channel so that I can hear in stereo. Okay, so that's the cable we'll use. So I didn't use the right schematic symbol there for that. Sorry. The one I drew is a mono. Okay, so this would be a tip sleeve connector, which is really all we're using it as. We're going to end up wiring it together. I know. You know, nobody's perfect. But man, I'm trying to be, to quote the great Mike Tyson. Okay. So here's the circuit we're going to build. I built it, and then here's my daughter's MP3 player. It's like an old school MP3 player. It's not a phone or anything, but you can go ahead and use your phone if it has an audio jack. For those of you with Apple products that don't have an audio jack, I don't know, you made some decisions there, didn't you? And now you don't have an audio jack. You could also use the audio jack if you have one out of your computer and you want to try playing some music out of your computer. Anything like that. It's an 1/8 inch audio jack. So here's the circuit. I thought it was worthwhile. I wanted you to see how the audio jack got plugged into the MP3 player. It looks like she was listening to some country music, so I apologize for that. But she's my kid, and I lived in Alabama for a long time, so it rubbed off. Is this backwards? No. Okay. I thought it was worthwhile to look at the SnapKit circuit. I think this is experiment number 60, if I'm not mistaken. So you can even just like pull out your book and look at experiment 60. There's so much going on in this circuit. It's going to take you a little bit to build. But I think what was good was these black numbers here. If you haven't done a lot of snap circuits, these black numbers tell you the vertical order that things are in. So like start with the ones that are 1, and then go through and put down the components that are 2, and then I think there's a couple of them that are 3. Okay, and that's going to help you stack everything up correctly. There were a couple of these little buttons that were needed to make things level. So those are those little 1 snaps together. Okay, so I'm going to leave this up. It is experiment 60. I'm going to totally double check that now that I keep saying it. If you want like the high quality from the manual. Yep, that's it. Okay, and that's going to be our little transistor circuit. Once you build it, and a couple of you start saying that you're good, I'll talk you through using the multimeter for how to bias it. All right, now you're just showing off, Casper. Took me longer than that. Come on. If you're done, go ahead and plug something into it and see if you can get some audio out of it. And then play with the potentiometer and see what it sounds like. Oh, I'm sorry to hear that, Casper. What else would have an audio jack? You don't have one on your computer? Is that an old-fashioned thing? I don't know. My computer's only 3 years old. It's broken. That stinks, man. Next year we'll send you with MP3 players. It's a little gray wire, Shams. Here, I'll scroll up. I think it's probably easier to see in the photo than if I just hold it up. Yep, there you go. All right, Casper, I'm gonna have to do it myself then. I'll play it over the microphone. I'll inflict country music on y'all. Which means I should probably make my circuit work again. Yeah, there we go. Still works. It's a big one, isn't it? It's working. Sweet. Nice, Shams. I love it. All right, I'll give people a little bit longer on it. That's cool. Okay, give it a go. The mad scramble to find something with a 1/8 inch audio output. What else would have it? Like, I think I have a Roku remote that has it. If you have a Roku. If you have an old, oh no, you're not gonna have an old CD. Nah. Who listens to CDs anymore? Um, it's the same jack that was on cassette players and CD players and all that sorts of stuff. Your TV set might even have one in the back if you have a LCD, but then you got to get to the back of the TV. Don't break anything. I don't want to be liable for that. Nice. Sounds like it worked. Woohoo! Cool. All right, play with that slider and see. Tell me what you hear as it changes. Oh, no wonder they won't give you anything that plays music. All right. Let's see if Juan and Josiah Chase hasn't been active in the chat. And I'm sorry my Spanish isn't better, Alfredo. Yeah, it's not a oh, we're not selling this thing. It's not, you're not going to make money off it. It's not a really good amplifier. Uh, but but um, but I think I'm hoping that it demonstrates the concepts. The farther you push it down, the quieter it gets and choppier. Yep. When we call that clipping, that kind of chopping. The farther up you push it, the choppier it gets, but stays the same terms and volume. Right in the middle seems to be the sweet spot. Spot on, Josiah. Spot on. Yep, you absolutely want it right in the middle. Okay. And that was a really good description of it. I like that. Yep. Okay, so, and this is actually something I'd have to do when I would repair stereos. What you're dealing with here is some signal going into the amplifier. This is kind of the generic symbol for an amplifier. Okay, and we want it to look the same as it comes out. So when you drive it through the amplifier, we're going to add some DC offset. So we're just going to slide the signal up or slide the signal down. And we need that to be the case so that some current is going to flow through the speaker. So if you drive the signal too far up, then you're going to hit the maximum value. So this might be 6 volts here. So let me get, this might be 6 volts because that's the highest voltage that we can have in the circuit. I'll try to get this above my head. Okay, if I drive it too far down, it's going to get quieter and you're going to start getting this clipping on the lower side. Okay, so rather than having the full sine wave come through, you're just going to have the top halves. Okay, too far up, you just get the bottom halves. Okay, so you want it somewhere in the middle so that the speaker can push out the same distance as the speaker can push in. So let's do that with the multimeter. And this is something that I would do when I repaired stereos. So some of the older stereos, you had to adjust the biasing. And the biasing was controlled by a resistor, a potentiometer just like this. And it's controlling how much current flows through the transistor when it's what we call quiescent, so that the input signal from the MP3 player is quiet. So quiescent is the fancy word for quiet. So when the input signal is quiescent, we still want this transistor on to the right amount. And we do that with this potentiometer. Okay, so you're going to take the multimeter. There it is. You're going to take the multimeter and you're going to set it to DC 20. Okay. DCV 20. And then you're going to connect the red probe. Let's see if I can draw it here. You're going to connect the red probe here. It's a horrible arrowhead, but it is what it is. Red probe. White is not going to be a good color here, but let's see what it does. And connect the black probe here. White's not. That's horrible. I guess I could just use black. Let's just use black. Right. Right. And black probe there. Okay, and you want it set on DCV 20. Okay, and the goal is to get that voltage, the voltage across the transistor, to be half of the total voltage. So you want to set that to 3 volts by varying the potentiometer. Okay, so give that a go. And then that's going to be spot on in the center. And it should sound fantastic. I'm going to do it along with you. Okay, so I'm going to set mine up. And that's on. If you can't hold everything, you may try alligator clips from the solar kit. Yeah, I don't have enough hands. Okay, so I got mine set to 3, 1.1. So that's a bit on the low side. So move the slide switch, or move the potentiometer. Right, move the potentiometer until you get it set around 3. Because then you too can listen to the sweet, sweet sounds of Alabama. Alright, 1.06. Is it not varying more than... I'm starting to wonder if your meter's messed up, Shams. Because all your numbers are off, but you said it was working, so it can't be that bad. Oh, we'll see how long YouTube takes to take it down, Juliana. Would you rather I sing? Honestly. I used to sing my kids to sleep, and then they got old enough and they went, "Yeah, we don't want you to sing anymore." So I took it personally. I didn't think I was that bad. Let's see. So I don't know if this comes through, but this is the clipping on the low end. And it kind of sounds like a fuzzy 1.03. Yeah, something's going on with your meter, Shams, I think. I don't know what to tell you. And it's been consistent through some of these experiments. Okay, so there's the clipping on the low end. Now it sounds clear in the middle. All the way up, I can hear a little clipping. I bet that's not coming through the microphone. But it is getting a little fuzzy. Okay. All right. So, and I think Josiah's description was just fantastic of what he was observing. That was great. Okay. Well, let's see. Where is that? All right. Which one are you? Which one are you? How you feeling? 4? Okay, cool. 4 is fantastic. I love that it worked. Like, that's great that you got it all working. So, and you're doing... Shh, don't tell him you're doing a little better than some of my undergrads. So, I'm happy. I really hope I get some of you in class. So, we should probably do, like, selfies with... You did selfies with the gliders, right? We have no evidence of doing electronics. If you want, go ahead and take a selfie with your circuit and send it to Professor Amaya. Not me. Send it to her. You took a video? Cool. Oh, awesome. Yep. That's great. Anything we can do to kind of promote and show that y'all have been just wonderful this week. So I want to share that with people. Okay. Well, I thought that was going to take us the whole time. So I didn't prep anything after this. I could lie to you, but I'm not going to lie to you. I wanted to look at integrated circuits. I guess we could look at integrated circuits a little, and kind of just talk about them for a little bit, and then we'll do the survey and wrap things up, and hopefully we meet again further down the road. Let me turn off the MP3 player. Turn off the MP3 player. Otherwise she yells at me. And I'm going to turn off I'm also going to slide the slide switch so that I turn it off so that I don't kill the batteries. Alright, and let's, the snap circuits comes with these two integrated circuits, and they have a U for a designator on here. This one's U27 and this one's U28, and the U comes from the abbreviation for a microchip, so we use a lowercase mu for microchip. And let's see here, I gotta write on something. Okay, so we use the lowercase mu to mean micro, and we use that in front of microchip. Okay, so that's why it gets a U designator. 10 out of 5. Cool. I love it. I love it. no matter how long I study and no matter how long I design and practice all this stuff, I still love when lights blink and music comes out of something or a motor moves. Like, it's still the most satisfying thing in the world to be like, it worked. It's such a great feeling. So I'm happy that you're getting some of that too, because I still love this stuff. All right, so these microchips, I didn't dig into them too far, really because they're a little harder to talk about, kind of fundamental principles. And my goal this week was to it's the best feeling in the world, Shams. So I usually joke and I say my mom's real proud. She is. I love it. I love it. So it's a little hard to talk about the kind of fundamental principles with these things because they're really complicated devices. Even though it's like plastic and it's got snaps all over it, it's hard to talk about voltage and current and resistance and transistors turning on and off because there could be hundreds, if not thousands, maybe even millions. Oh, man. Millions of transistors in here. And it's kind of hard to pick out what's going on. Especially with these two. These are audio microchips. So they do a lot of analog stuff, and it's a little hard to visualize that, and you don't have the equipment to do it, unfortunately. If we were in my lab, we would totally have the equipment to do it. I even have some of it here in my basement. I'm not sure if you heard that, but I think one of my children is going to fall through the ceiling. So I would love to hook these up to oscilloscopes with you and logic analyzers and see what's going on. But unfortunately, we can't do that, which is a little frustrating. But maybe next year I'll send out oscilloscopes to everybody. Those are expensive, but we can try. But let me see if I can pull kind of just a brief overview of integrated circuits. And then we can look at that quickly, and we'll do the survey and wrap things up from there. Oops, wrong class. Okay. Let me see where I talked about integrated circuits. Yeah, Shockley, Barden, and Brayton. Here. Let me just get this up into a window that's good for you to look at too. Oop, there we go. It's supposed to become full screen. Yeah, there we go. Okay. So this is all from a lecture that I give regularly. Shockley, Bardeen, and Brayton. These are the guys that made the transistor. And Shockley usually gets all the credit, and Bardeen and Brayton are the other two guys that I can't even remember. So this is the first transistor. And this is all related to integrated circuits, because an integrated circuit is just a bunch of these put together. So a lot of times my seniors, when they're working on their capstone projects, will build their projects and they'll go, yeah, but it doesn't look pretty. I want to like clean it up and stuff. And I usually show them this picture and I say, lots of sweat and tears, I think. That's how these ideas come to mind. But I usually show them this picture and I say, this is the first transistor. This thing has revolutionized our world and it is ugly as sin. They said, so it doesn't need to look pretty. It's a prototype and it just needs to work to demonstrate that you should graduate. So that usually makes them feel better, hopefully. But that was back in 1947. So if you're thinking about historical stuff, that was right after World War II. So World War II, all of the electronics and radios, they were still tubes, old vacuum tubes, before this was widely available to take its place. So the first commercial use of the transistor was for radio, and these were all old tube radios, and they were really big, and they used a lot of energy because a tube had to heat up the grid for the electrons to break free from it. So these were big. They're not even the biggest. Some of them were like full console size radios, just a radio. Think about what's in your pocket with your cell phone nowadays. It's pretty crazy. But the first commercial use of a transistor was this little transistor radio, and they say it could fit in your pocket, but it was like you'd need pretty big pockets. Sorry, ladies, I'm starting to understand the lack of pockets better, thanks to my daughters and my wife. But this only had a handful of transistors. I think there was one or two of them in there, but it could run off a battery. It was a little more efficient, even though it was BJT transistors. It was a little more efficient than a tube. It's a lot more efficient than a tube. But there was only a couple transistors, and they were all discrete parts. So here's the inside of it, looking really close at it. And you can see there's a bunch of resistors, and then I think it looks like there's 3 transistors in these weird packages from an era before I was born. The capacitor is here. This was the tuning capacitor. So it was either Casper or Josiah that said when we were talking about capacitors what the dielectric could be. This is the capacitor with an air dielectric, so that you could turn the screw and it would actually take the plates of the capacitor and move them back and forth, and that's how you would tune in different stations. So that was an air dielectric capacitor, but it was all discrete components. And that's what we've been building all of our circuits out of, is discrete components. And I have an assembly video. I'll leave that. It's pretty funny. Still using discrete components. Sony, so Japanese company now, came up with a portable television. And here was their portable television. I think it's about the size of a small, like, drink cooler. It was pretty big. It had buttons on here. I don't know if you can make that out over the feed, but it says AC, DC, and off. So it had like a big button that you could press to plug it into the wall, and a big button that you could press to like have an additional battery that it ran off of. And this was 1960. And it had a lot of components as well. It had 1, 2, 3, 4, that I can count, 4 circuit boards that all had to be put together. And this was like a portable television. It was the wave of the future, that you could carry this thing around with you. Pretty bad. The other problem with this is it was notoriously unreliable. The thing just broke down. It was so complicated, and all the parts were so fragile that it would just break. It wasn't very good. So like nowadays, we usually think of Sony as being like a good good company in terms of quality of electronics, but they started off pretty bad, and this was one of their products. So with all of those discrete components, putting it together was a mess. Reliability was junk. So Kilby, so now we're back in the U.S., Kilby came up with the first integrated circuit, and that was in 1958. So the timing of that's interesting, right? They were figuring out how to build integrated circuits, but there were still commercial products being designed using older technology, which isn't unheard of, right? This was in a lab in 1958, so it certainly didn't hit prime time. And then here's another good example of like a super ugly experiment. This was the first integrated circuit. Okay, and here's a schematic symbol for that integrated circuit. At the beginning of the week, if I put this in front of you, you might not have been able to pick anything out, but I'm hoping that now, after today, certainly you can say, hey, look, there's a BJT transistor. Okay, and a couple resistors. And then this one's funny, it's a hybrid between a resistor and a capacitor. That's not a component you run into very often. But you can kind of pick out what that circuit looks like as a schematic, and then you can look at the physical realization of it. It's junk. And then there's Kilby. Look at him with those nice aviator glasses. Okay, so that became commercialized in Texas Instruments. That's who Kilby was working for at the time. What's called a multi-vibrator circuit, which is really just a fancy way to say it's a oscillator that we can change the frequency of. So here's the first commercially available integrated circuit, and it's the Texas Instruments multi-vibrator number 502, and that came out in 1960. So any kind of computer that needs a clock signal, you can build it out of an integrated circuit like that. The 502 is a predecessor to the 555, And if you do anything with electronics long enough, you'll run into the 555 timer. So this was kind of the precursor to that, but it was the first commercially available one. Okay, and then we made it smaller, and we made all the transistors smaller, and we managed to fit millions. I'm on a logarithmic scale. Okay, we can fit millions of them, if not billions of them, on a little chip. So we've decreased the transistor size. So think about how many transistors are in this ARM processor. Yeah, absolutely. Yep. There's a ton of integrated circuits in the PC. This is a microprocessor. It's an ARM processor. So it's not necessarily in a PC, but it's in a lot of embedded devices. It's a really good processor. That's pretty common. Think about that size. It's hard to get a judge on the size of this, but this was a single transistor with a couple resistors around it. Right? So we went from one transistor with some other components around it to being able to fit billions of them in a chip. So it's pretty crazy. Yep. Yeah, you gotta ground yourself and all that stuff. I remember doing that with my dad too. That's cool. I was in third grade when my dad bought our first computer, and it was a big deal back then. It was in the 80s. So we figure out how old I am from that. And he was so excited that he had gotten the computer that he came to school and got me out of school early and brought me home so I could build it with him. So, because he knew he wanted me there with him. So that's cool. I'm glad you did that with your dad. That's a good thing to do. So I'm pretty sure my mom was pretty mad at him when she found out he took me out of school. So anyhow, that's probably long forgotten, hopefully. So when you look at these devices, I have no idea what's inside of them. Yeah, you should see my basement right now. I've got snap circuits everywhere and the solar kits over there, and yeah, it's a mess. So I can relate to that. So I don't know what's inside of these. I'd have to really kind of dissect them. It might be fun for me to break it apart. But there's an integrated circuit, and that integrated circuit can have a lot of signals coming out of it. So if I'm looking at the voice changer integrated circuit in this red kit, I see two inputs for a microphone. So mic plus and mic minus. So that's going to take probably something similar to the output of your MP3 player and put those in there. It's got record and play. So those might be button presses. So those might be digital signals that you create with a button so that you can control what it's doing. There's a SPD. What do you think that is? Speed. Might be a digital signal as well from a button. And then there's a speaker out over here on this side. So speaker plus and speaker minus. I'm guessing that's what SP plus and SP minus are. So there's some analog stuff going on. There's some digital stuff going on. And I think it'd be pretty cool to stick an oscilloscope on both of those, but I don't have an oscilloscope with me. They're all quarantined on campus, and otherwise I'd love to share that with you. Okay, but that's an integrated circuit. By all means, check out the manual and play with it. Right, there's nothing wrong with playing with it. There's 188 projects to play with, so I'm hoping that you're getting comfortable putting them together and kind of thinking through what the voltage is doing, what the current's doing. That's my hope for you. Okay, water alarm, high and low light. I don't know. Looks like fun. I'm going to build some of these with my son now that I can be a little sloppier with the kit. I don't need it for demos for you. This one's interesting to me. The keyboard. I don't know what's going on inside here. I really want to play with this one, and I really want to hook it up to my Logic Analyzer. Oh, the yellow even disappears a little. Because I think that might be neat. And since this one's a sound kit, I think you can play some music with it. So I don't know if it's an analog signal or a digital signal coming out of that. So I'm a little curious. So I'm gonna think about that one. You should think about it too as you build. Okay, so it does beeps and boops. of course, Casper's already played with it. Yeah, so it might be different frequencies, but it might still be a digital signal coming out of it. That's just bouncing back and forth between discrete values. I love it. Okay. So, whoops. So that's that. And then, so we're a little early, but I do want to have you fill out that survey that Professor Amaya mentioned. I think she posted it. I got to go find it. She posted it in a couple places. Nope. Ah. Here we go. I think it's like all the way at the top of the text feed, but there's the Google Doc. I think that'll work for you. Let me try it again. Yep. Okay, so you know, we're when I hand out my course surveys, I usually say constructive criticism is welcome, destructive criticism is usually laughed at and passed around the classroom. But tell us what worked and tell us what didn't. This is certainly our first time doing this virtually, so I would love to hear feedback for that because it will only help me teach better in the fall. And that's something that I'm worried about. I'm trying to make sure that I can still teach effectively like this. So whatever you can tell us, we're happy to do. Any pictures, any videos, send it to Professor Amaya. If you need to reach out to me at any point, I'm not sure if she's given you my contact information, but you can get me on my email, broderick@ccsu.edu. And I'd love to hear from you. And when we all are back on campus, whether it be this year or next, by all means, look me up and swing by the office because I'd love to meet in person. So take a few minutes and fill that one out for us. So, and only she knows how to see the results. I have no idea. So, just let me know, I guess, when you've completed that. Go back to the Star Trek bridge too. Cool. Thank you, Casper and Shams. Great. Thank you, Juan. So hopefully you're working on it, Josiah, Chase, and Alfredo. Nice. Off your little amplifier. I bet she's got some dubstep on this MP3 player. Just saying. She's got a pretty wide musical taste. A little bit from me, a little bit from her mother. You know. Cool. Thanks, Juliana. Oh. Yep. Cool. 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 All right. Let's give him a few more minutes and then wrap it up. And cool. Thank you, Josiah. All right. So Chase and Alfredo, as long as you're still working on it, you know, we certainly don't need to finish it now. But you know, go ahead and take that survey. The more answers we get, the better. And it really is helpful to us. I know some faculty members don't read the reviews. They're not good faculty members. But I know that both myself and Professor Amaya, we think about our teaching a lot. So we really count on feedback whenever we can get it. So thank you all for filling that out because it's going to help us make things better. And that's what we want to do. We're pretty committed to that. And I think that's why we work well together. Okay? So I'll stick around. I'll stick on the chat. But I'm now the presenter. Look at me. I'll stick on the chat, but I think that wraps it up. I hope you've had a good week. The gliders were cool to watch. I'm kind of jealous I didn't get one of those kits to play with, but maybe I'll guilt Professor Amaya to handing me one of these weeks, and I get to play with those too. And then I hope you walked away feeling a little more comfortable with the basic concepts of electrical stuff. And I know a lot of you said that you were interested in mechanical. We just started an electrical engineering program at Central. We have 2 students right now, but I would love to see you there if maybe you've you know, gotten an interest or changed your mind a little bit. Even if you just want to talk about your careers, I'm more than happy to do that with you. Okay? So, like I said, I'll stick around, but if there's nothing else, it's good to meet y'all, and hopefully we meet further down the road. That's a good question. I have no idea. The program. Electrical engineering. It's a bachelor's, BSEE. That's great to hear, Shams. Thank you. That's what we're trying to do. The Steam game, MHRD. Yeah, something tells me that's going to be right up your alley. I'm most of the way through it. It gets pretty complicated, you know, but it kind of builds you up. When we design logic circuits, we frequently use a language called hardware description language, and there's different flavors of it depending on what processor you're using. And we describe how the logic gates are connected to each other using HDL. And what the game allows you to do is they give you a specification, and then you write the HDL to make that happen. And as you're progressing through the game, you're building more and more complicated structures. And ultimately, what you end up doing is designing a whole processor based on that specification. So, like, if you can do that, you're in good shape. Like, you're in really good shape. So, that'd be cool. Take care, Juan. Thank you so much. So, I could even bring it up, honestly. Let me see if I can find it. HRD. I think it was like $7 or something. It was on the cheaper side. That's great, Josiah. That's what we like to hear. So thank you so much. That's how I got started too. My grandfather was a radio man in World War II. He flew planes, and he fixed the radios using the old tube circuits. So that's how I got started, was playing with stuff with him. Yeah. So anyhow, so the whole interface of MHRD is made to look like an old DOS computer. So you got to work your way through it, but you like write the code for multiplexers and demultiplexers and all that stuff and put it together. So yeah, check it out. I'm not even sponsored by them. I wish I was, but it's pretty cool. I teach. Oops, let me do that privately. No way, there's another Mr. Broderick. That's awesome. There's a handful of us, but we don't really interact with each other. It's not an uncommon name, but it's not so common that you run into a Broderick every day. That's fantastic. So I teach circuit analysis courses. I teach some capstone courses. I've been teaching control theory, which is what I studied in graduate school. It's what I like to do. I've in the past I've taught digital courses as well. Let me see I can pull up my website, my course website, so that I remember what I teach, because it depends on the day. I also teach a course on electronic design automation, which is how to fabricate PCBs for electronic components. So linear circuits is kind of the intro to circuit analysis. I gave you a little bit of it. I gave you a taste of that this week. Electronic design automation is how to fabricate printed circuit boards. That presentation that I pulled quickly came from here, because we talk about how things are fabricated in that course. Electric systems analysis is how to build filters and how to work with any signal. When I'm teaching circuit analysis, I like to say I want you to learn how to analyze any circuit. And then when I'm teaching electronic system analysis, I say I want you to be able to analyze any circuit responding to any signal. And over the course of those 2 semesters, I can usually get that done. I've done capstone for a number of years, so that's kind of helping you manage your way through projects. In the past, when I taught at Auburn University, which is also where I did my master's and my PhD, I taught digital logic circuits. I absolutely loved teaching digital logic circuits. That's a really fun course to teach, because the math isn't outrageous. All of you could take that course right now and you would do wonderfully. The math isn't outrageous, and we can build things and you can see them work really quickly. And so, like, it's a great class to get it's a great class to get an immediate result and kind of get hooked on that feeling that we were talking about earlier. And then I got to teach controller dynamic systems this year, so I was pretty happy about that because that's my field of study. I've taught programming in the past. I was a software developer for 5 years for an insurance company, and that's I think that's helped me throughout my career as an engineer. Was having that strong background in programming. So I've taught some classes in programming as well. I feel like I'm missing a few. I've taught a lot of classes. Surely I've taught others. Anyhow, I taught a graduate class at Auburn on how to. What is that website? That's my website. I'll give you a link. That's all public stuff. This is my teaching website. If you want to go poke through any of those materials, you're more than welcome to them. And it's a bit of a mess, honestly, because of the spring semester. When we went online, like half of some of the classes are on there because I started having to generate a lot more content. So you'll see some of that. Oh, that went privately. I'm happy to share that with everybody. I'm still getting used to the WebEx interface with the chat. It's a little different, so sometimes I don't see when things are sent to me one-on-one. So, yeah, don't look too long at that picture. That guy's ugly. So you can see some of the papers I've written, all that fancy stuff. That's all out there, and then kind of a truncated resume. That's about it. All right. Anybody got good plans for the weekend? Looks like the weather's going to be kind of yucky. Yeah. Yep. Video games. You sound like my kids, but my kids are too young to be stuck playing video games. Cool. Ooh, nice. Always good to have family with a boat. We got an inflatable pool for the kids because we're not leaving the house too much this summer, as I'm sure all of you are. So we fill that up and let them splash and get messy. So we'll probably do that over the weekend. Try to get them good and tired. Exactly. That's the best part about being a dad. Cool. All right. Well, don't hesitate to reach out. If I can do anything. I don't know where y'all are in your high school careers, but I'm happy to offer guidance when I can. And if you all end up at Central, I think that'd be the best thing in the world. Yep, it's got a cool water slide and everything, and so not quite deep enough to do diving, but they're not quite there yet anyhow. So yeah, it's pretty cool. It was kind of out of necessity. Like, what are we gonna do with them for this much time? They're gonna go crazy, as I'm sure we all are. So cool. All right. So if you haven't filled out the survey, shoot me an email just to say hi. That's not bad. A street runoff stream. I don't know if I'd want to swim in a street runoff, but it's better than nothing. Thank you too, Josiah. You're going into 9th. Cool. That's awesome. Well, shoot. I hope you keep coming back, and I hope I see you in a few years. I love it. I bet it is. I bet it is, Casper. Good to see you, Josiah. Yeah, we've got a swampy one in the back that I wouldn't swim in, but during the spring it gets high enough, but that's about it. And that's cold. I'm not going in it. Ooh, yeah. Well, you learned your lesson, didn't you? All right. All right, everybody. I'm going to sign off. Thank you so much. And I hope you have a good rest of the summer.